أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. بسم الله والحمد لله والصلاة والسلام على سيدنا مولانا رسول الله وعلى آله وصحبه ومن والاه. Okay, so we have given two lectures. We have given a lecture on scientific concepts and one on scientific theories. This lecture is going to be on scientific models. So, what are scientific models? The scientific models are central for scientific inquiry. Scientists dedicate considerable time to creating, testing, comparing, and refining models. The philosophical study of models has grown significantly, and this lecture will explore various aspects of scientific modeling, including their semantics, ontology, epistemology, and relation to theory, as well as how models impact broader philosophical debates within science. That's going to be a bit brief. Now, let's start with the semantics of models. Many scientific models serve as representations of specific aspects of the world, known as target systems. So examples are the billiard ball model of gas, the Moore model of atoms, the Lotka-Volterra model of predator-prey interaction, and scale models for objects like bridges or cars or ships. Now, one of the fundamental questions when it comes to models is, what does it mean for a model to represent a target system? Now, this is admittedly a difficult question to answer. So instead of delving into this general issue of representation, which we might do in a different lecture, we will discuss different types of representations that are important in model-based science. These include, let me try to move this here. Scale models are okay, and this includes scale models. So what are these? Well, these are downsized or enlarged copies of target systems. For instance, we have a wooden car model used in a wind tunnel to study aerodynamics properties. While they while these models aim to be faithful replicas, obviously faithfulness is always limited. So for example, a wooden car model may accurately represent shape but not material. Furthermore, the relation between a model and target properties is often complex and nonlinear. For example, the water resistance of a ship model cannot be simply scaled up to find the resistance of a real ship. Next, we have analogical models. These models establish similarities, so they rely on analogy. These models establish similarities between different systems. Examples include the billiard ball model of the gas or of gas and the hydraulic model of economic system. When we think of analogical models, we're thinking about shared properties. Properties are shared by the model and the system, and similarities between properties and the resemblance of relations. So an analogy between sound and light is based on similarities like echoes being similar to reflections. So when we try to involve an analogy between sound and light. Analogies can also be based on the same pattern of abstract relations or formal setups, such as formal analogies between swinging pendulum and an oscillating electric current. Here we're not concerned with similarities at the level of properties, but at the level of pattern of abstract relations or formal setups. Now, analogies can be positive. Here we would be focusing on the positive as in shared properties, and negative as in non-shared properties, and neutral properties that are not yet determined. So we're not sure whether they're shared or not. Neutral analogies or the neutral aspects of analogies are important in research as they can suggest new questions or hypotheses. We can test whether this presumably neutral property is actually a positive one or a negative one. Next, we have idealized models. These models intentionally simplify or even distort complex systems to make them more tractable. Famous examples include frictionless planes, point masses, and perfectly rational agents. They are crucial for handling systems that are difficult to study in their full complexity. There are two main types of idealization. We have Aristotelian idealization and Galilean idealization. Aristotelian idealizations remove properties deemed irrelevant and focus on a limited set of properties. Whereas Galilean idealization deliberately distorts aspects of the system, such as models of point masses or frictionless planes. Galilean idealizations can be controlled or eliminable by removing distorting assumptions. So after we have put or distorted certain assumptions, we can try to remove them and see how it goes. But some are actually ineliminable, where the removal would dismantle the model entirely. Now, idealization can be understood as ideal limits. The limits of a system can go. Where the closer a system comes to the ideal limit, the closer its behavior should be to the system at limit. So, almost like representing a system at its limit. However, singular limits can occur where this behavior differs. Many models combine Aristotelian and Galilean idealizations. So sometimes we remove certain properties when we're modeling, sometimes we deliberately distort others. Sometimes we do that as well in the same model. Now, Galilean and Aristotelian idealization are not mutually exclusive, which we already said. And many models exhibit both in that they take into account, this is the Aristotelian part, they take into account a narrow set of properties and distort them. This is the Galilean part. Consider again the classical mechanics models of the planetary system. The model only takes a narrow set of properties into account and distorts them. For instance, by describing planets as ideal spheres, which they're not, with a rotation symmetric mass distribution, which is not the case. Next type of models, we have toy models. These models are extremely simplified and distorted representations of their targets that often represent only a few causal or explanatory factors. Also, the Lotka-Volterra model in population ecology is a toy model. Toy models are not usually strong in predictive power and empirical adequacy and might serve other epistemic purposes. They may be considered caricatures that isolate and distort salient features of a system. It is debated whether these highly idealized models can still be informative representations of their target system, because they're very idealized, they're very distorted. Similarly, we have what is called minimal models. So similar to toy models, these are highly simplified models, so simplified that some might argue they're not even representational, and they lack similarity, isomorphism, or resemblance to the world. Some economic models are considered minimal. Minimal models function as surrogates for real systems, even if they do not represent them. So they help scientists learn about macro scale behavior of a system, even when the micro scale behavior is very diverse. Proponents of minimal models argue that explanations provided by minimal models is possible without common features. This is based on the idea of a system and a model belonging to the same universality class, i.e., a class of models that exhibit the same limiting behavior even though they show very different behavior at finite scales. Next, we have phenomenological models. According to one common characterization, because we have more than one characterization of phenomenological models, according to one common characterization, these represent only observable properties of targets and avoid postulating hidden mechanisms. You could think of them as surface level models. Another characterization considered them as independent of theories. They act as mediators between theory and the world. We will say some more on that when we discuss the relation between theory and model. They are not according to the models as mediator view, they are not derived from theory. They are independent of them. And we'll say some more on that in a few. Other types of models are explanatory models. Now, these models are not proposed to learn about a specific target or phenomena initially, but no, sorry, they are Ya Allah. They're exploratory. I'm just stuck at explanatory. Okay, they're exploratory models. So, as the name says, they're meant to explore. So these models are not proposed to learn about a specific target or phenomena initially, but as a starting point for further explorations. They can provide proof of principle and suggest how possibly explanation. So explanations is a big field, it's a big topic, but we will not get into that today at least. We might have 1 or 2 sessions on explanations. Such models do not give an accurate account of the behavior of an actual population, but they provide the starting point for the development of a more realistic model. So you have, let's say, a target system, or let's say a phenomenon that you're trying to model. You're not sure how to approach that. You start with an exploratory model. So you try to explore what features are there, and then you try to provide something more realistic. Next, we have models of data, and we have discussed that in theories when we discussed what is scientific theory. So these are corrected, rectified, and idealized versions of these are corrected, rectified, and idealized versions of raw observational data. They involve eliminating error and presenting data neatly through data reduction and curve fitting. For theory-first philosophers, these models are tested against theories instead of raw data. So they are not confronted. Even those that are theory-first philosophers, a theory is not confronted with raw data. They're usually confronted with models of data. The construction of data models requires statistical techniques and raises methodological questions about data points removed and the types of curve to fit. These categories obviously are not mutually exclusive, and a single model can fit into several at once. Now, the way model represents its target is crucial to how model can be used. Having said a little bit about types of models, now we move to ontology. We said we're going to talk about semantics a bit, then we're going to move to ontology, then epistemology. So in ontology, the question of the ontological status of model discusses the ontological status of models. So what kind of an object are models? Some argue that models do not form a distinct ontological category and that anything can be a model. This is a quite liberal construal of model. Others believe that it is essential to analyze the different ontological kinds to which models belong. The objects that commonly serve as model are diverse, and we will say a bit on each. So we have physical objects, we have fictional objects, we have abstract objects, we have set theoretic objects, descriptions broadly, equations, or a combination of all of these. Now, this discussion has implications for our understanding of models semantic and epistemology, because the question of semantics and epistemology and ontology are tightly linked. Now, model ontology, physical objects. So the kind of models that are physical objects. These are also known as material models. So they're material. They're out there. And examples include scale models of ships and bridges. Another example is Watson and Crick's metal model of the DNA. Model organisms in biological sciences, such as Drosophila and E. coli and whatever. These objects are generally not ontologically problematic because they raise similar issues that metaphysicians encounter. So when metaphysicians discuss, let's say, ordinary objects, well, some of these or all of these are ordinary objects in that they are material objects that exist out there. Now, after material objects, we have fictional and abstract objects. So many models like the Bohr model of the atom are not material. The fiction view of models consider them similar to literary fictional objects. So the model of the atom is seen as a fictional object, like, for instance, Sherlock Holmes is a fictional character. This view aligns with scientific practice where models are often discussed as though they were objects. However, fictional entities also pose philosophical challenges. Some argue that comparing models to fiction has a heuristic power in tackling these issues. So if you treat them as fiction, it has a heuristic powers. And we also have dualist accounts, which suggest a model is an abstract object that also stand for a possible concrete object. Other perspectives interpret models through a pretense theory. So we're pretending, viewing models' description as props in a game of make-believe. So we're pretending that such and such. The models exist within the scientist's imagination. Others reformulate this view, considering model description and their content as the model, which support a realist view of models since descriptions exist. So they consider model description, their content as the model. So the description and the content form the model. And this is thought to be a realist view because, well, the descriptions do exist. Critics of the fiction approach argue that calling models fictional diminishes their epistemic standing, suggesting that they are false. It's almost intuitive. When you think of something as fiction, you're thinking that it's not real. And this is why critics say, well, the moment you take it to be fiction, the moment is you concede that it's not real. However, proponents of fiction view argue that the defining feature of a fiction is not its falsity, but that readers imagine the described event. So this is where proponents of fiction respond. They say, the emphasis when we speak of fiction is not on falsity per se, but on the imagined, on the imagination in the description of the event or behavior or thing. So we might imagine something, and that something might exist. So since the emphasis here is shifted from falsity to imagination, we can imagine something that is real. So it is not the case that a fictional view by definition leads to falsity. Now, abstract models are abstract entities, and there are multiple characterizations of abstract objects, and also understanding of what they are. So a Platonist, for instance, believes that abstract objects exist eternally in a world of form, let's say. Whereas an artifactualist, as the word literally says, so it's an artifactualist, is a person that believes that these are brought into existence through a creative act. So they're artifacts. And they disagree. So the artifactualist says they're not eternal. Next, we have set theoretic structure. This perspective views models as set theoretic structures, tracking back to Patrick Supi, and we discussed some of his views in our discussions of scientific theories. And this aligns, like I said in scientific theory lecture, this aligns with the semantic view of theory. However, this view is also criticized for being unable to accommodate many types of models. We have numbered, I've mentioned a number of different types of models, and to restrict models to set theoretic structures is too restricting, actually, because many of these are not structures. So this is one of the criticism. Another criticism is that these models are not really the kind of things that are used in research. And this is something we also mentioned in our lecture on scientific theories. Furthermore, some argue that they cannot be representational. So let's say someone is using a model to represent something. And if we take this view and we take models as set theoretic structures, the objector says that these cannot be used for representational purposes, where we think of representations as, well, sharing a structure with the target. So if the model is a structural model that relies on set theoretic structures, then for it to represent a target system, that target system would need to have structures. But if we look around, what we find is we have substantive, i.e. non-structural targets. So unless the target has a structure, really has a structure, then we cannot use a structural model to represent it. And that's the problem. Next, we have descriptions and equations. A common view is that a model is a stylized description of a target system. It has been argued that this is what scientists display in papers and textbooks when they present a model. Now, the association of models with description faces similar criticism as those presented in the syntactic view of theory. So this also brings back to the lecture, our lecture on scientific theories. In what way? Well, first, a standard criticism of the syntactic view is that by associating a theory with a particular formulation, the view misconstrued theory identity because any change in the formulation results in a new theory. Remember, we said that the syntactic view takes a theory to be sentences. And the objection was, well, if you change any detail in the sentence, you would have a completely different theory. Well, this equally applies to the models as description equation, in the sense that whatever change in the description you have, you'll have a different model. Second, models have different properties than descriptions. For instance, the Newtonian model of the solar system consists of orbiting spheres, but it makes no sense to say that about the description. Descriptions do not have orbiting spheres. Now, having finished ontology, we move to epistemology. The cognitive functions of model. And models are essential to science because, like I said earlier, they serve different cognitive functions. They are used as tools for learning about the world, often through surrogative reasoning, which you mentioned, where models are studied to understand the real system. So what we study is not exactly the real system, but we study the model and we try to infer certain things about the system through studying the model. This is how they act as surrogative, as subject of or object of surrogative reasoning. This has given rise to what is known as model-based reasoning. So reasoning based on models. Now we start with learning about models, then we move to learning from models. But let's start with learning about models. Learning happens during one, model construction. So model building, it should be important to note, has no fixed rules. So the process of figuring out what fits together provides an opportunity to learn about the model. There are no blueprints to build a model. You're supposed to have a know-how and through trial and error and integration of different components. Two, we have model manipulation. So once the model is built, we do not learn about its properties by simply looking at it. We have to use it. We have to manipulate it. So two levels of learning about a model. We have learning through construction and we have learning through manipulation. Material models are relatively straightforward, being studied through experimentation. So again, when we spoke about material models, we said that they're the physical things that are out there. Well, you can manipulate material models, and you can do that through experimentation. So this is relatively straightforward. But the issue is with fictional and abstract models. How do you construct these and how do you manipulate these? Well, this takes us to the realm of thought experiments and conditions for a good and bad thought experiment. Yeah, learning about a model. Are we still in learning about a model? Okay, so computational models allows us to solve otherwise intractable problems and explore consequences. We said something about that earlier. If a system is complex, we might as well rely on something that is a bit more tractable, so we construct models. So computational models allows us to solve that, especially with powers of computers, and explore consequences. Computer simulations are important in various research fields for exploring the consequences of models that cannot be studied otherwise. They have heuristic values, in suggesting new theories, models, and hypotheses. However, they also have disadvantages because of the concrete nature of calculations and because they only allow the exploration of parts of the full parameter space. So the power of a new computer can also lead the power of a new computer can also lead to conceptually premature models, a reliance on misleading calculation, and changes to weighting of research goals. So in a way, we're held hostage to the power of the computers we use, and we might think that whatever results we get is the truth, although we're just limited by the computational power, or let's say this not approach. Anyways, we're limited by whatever system we have. Now, from learning about models to learning about target systems, or learning from models. Once we have knowledge about the model, this knowledge has to be translated into knowledge about the target system. Because remember, at the end of the day, when we're doing science, we're trying to learn about the world. And we said that in many cases, the model acts as intermediary. So at the end of the day, we need to translate whatever knowledge we get from a model about, or translate into knowledge about a target system. Now, this translation hinges on the representational function of a model, which we haven't said much about. And I said that we might as well present something on representations. I think this is really important. As well as the fact that different kinds of representations give different kinds of learning. So we have different types of models. We have realistic models, we have analogical models, we have idealized models. We spoke about these. And these lead to different types of learning about the targets. Always in the realm of epistemology, we have explaining with models. Some models are used to explain. However, this raises questions about whether they can do so despite their idealization. Remember, we said that we have idealizations, which are simplifications or distortions. So the question is, how can models explain if they have idealizations, i.e. if they have distortions? Now, some theorists request that explanations should be true. There are different theories of explanations, and many take explanations to involve truth. So those theorists that accept or request that explanation be true, some of them argue that idealization do not contribute to explanation. Well, because idealization does not involve truth. Others argue that idealized models explain when they leave out features that are irrelevant to a specific explanation. So I have a model, I have certain idealizations here and there, but when it comes to explanation, I'm relying on features that are not idealized. So there's no falsehood in. So we do not have to, it does not imply that we have falsehood out, if that makes sense. So I have a model, this model has features, some features are idealized, i.e. distorted, others are not, and if the explanation relies on features that are not distorted, then it's okay to accept an idealized model for explanation, says that person. Others emphasize that models need to accurately represent relevant causal relations in the real system to explain. Here we have a specific demand on causal relations in a system for us to accept that, well, a model accurately represents. Others highlight that models can explain by distorting difference-making causes. So some emphasis generally causal relations. Others are emphasizing specific kinds of causal factors, i.e. difference-making causes. Now, some argue that models are tools to show the relations that do the explanatory work. So almost like an instrumentalist understanding. Some theorists argue that it is the truth of the explanans that make a model explanatory. So we have an explanandum. An explanandum is something to be explained, and the explanans is what is provided as an explanation. And here we have theorists arguing that the truth of the explanand is what makes a model explanatory. Here we go back to the idea of explanations demanding truth. albeit in a more strong demand. Truth is what does the explanation. Other theorists pursue the line that false models explain. Okay, not only despite their falsity, everything we have been saying so far was can models explain despite their falsity? Now we have theories that say that actually models explain not in spite of their falsity, but in virtue of it. In this view, or on this view, models are the explanations. So the models themselves are the explanations. Others suggest models explain when details that characterize a system do not matter for an explanation. So we don't really care about the details here. We can explain, they did not really specify, but there's a huge literature on that. Here, what we care about, or what these people care about, is the explanatory power of a model. And this relates to the fictional nature of modeling for those who accept a fictional understanding. Obviously, there's a lot of pressure being put on, or a lot of emphasis being put on explanation, explanatory power, which are not clear concepts. So if it's not clear for you, it's because the very concept of explanation is debated, with different philosophers having different understanding of explanation and different conditions for accepting and rejecting explanations. Still in the realm of epistemology, we have understanding with models. So we spoke about explanation, now we speak about understanding. Understanding is for some taken as another goal of science in general, yes, and of models in particular. These people say or claim that models and the act of modeling as a process play a key role in this in understanding. According to these view or to these people, and they're not a single person, obviously. Similar remarks can be made about understanding. Similar remarks to explanation. So understanding does not have a single characterization. Different philosophers characterize understanding differently, according to different theories of understanding. Nonetheless, understanding is achieved when there is an epistemic commitment, so this is quite broad, to a body of information, which is grounded in fact and is responsive to evidence and enables inference and argument. So these are, I think, some minimal conditions which are good enough. So we have an epistemic commitment. Doesn't matter what kind of commitment it is. It could be belief, it could be something else, about a body of information. This body needs to be grounded in fact, i.e. in the world, and it needs to be responsive to evidence. We need to tweak or change when it responds to evidence, and it enables inference and argument. Some suggest that model can be used to understand independently of the ability to provide an explanation, while others say that understanding is directly linked to grasping. This is a technical term. Grasping of an explanation. The debate here is on whether or not understanding is connected to explanation. Some say, well, we can have understanding without explanation. Others say no, understanding comes after explanation. For instance, in the example here, we have grasping an explanation leads to understanding. What grasping mean is a different topic. Now, also we have other cognitive functions. So we spoke about different functions, but models also have other cognitive functions. So they're used in concept formation. This brings us back to the idea of our lecture on scientific concepts, and these are also used in theory construction, as well as other pedagogical values or functions. Now, models and theories. We said that we're going to talk about the relation between models and theories. So on one view, models are subsidiary to theories. To discuss the relation between models and theories in science, it is helpful to briefly recapitulate the notion of a model and that of a theory in logic. So in logic, we have a theory. And a theory is a set of sentences in a formal language. A model is a structure that makes all sentences of the theory true when its symbols are interpreted as referring to objects, relations, or functions of a structure. Logical models are sometimes also referred to as models of theory. for obvious reasons, to indicate that they are interpretations of an abstract formal system. Now, having that in mind, models in science sometimes adopt this concept of being the interpretation of an abstract calculus. It is important to keep logical models and representational models separate. So we have logical models, or what we said earlier, models of a theory, and we have representational models. And it's important to distinguish these two. Many scientific models are both logical and representational models. Here, instead of logical, we might say also interpretative model. So we might say interpretative model, they give meaning to the syntax, whereas representation or representative models, they represent a particular system. The syntactic view of a theory mentioned in the previous lecture retains the logical concept of a model and theory, viewing a theory as a set of sentences, as we said earlier, and a model as an interpretation of a calculus. The model is something familiar which helps to make an abstract the model is something familiar which helps to make an abstract formal calculus more palpable. The semantic view, on the other hand, dispenses with sentences. Remember, we said it does away with sentences and construct theory as a family of models, mathematical models, which are often seen as set theoretic structure. We said the language of semantic theory is mathematics and not meta-mathematics in the syntactic theory. Now, another understanding or another view about the relation between models and theory is that models are independent from theory. Now, in both the syntactic and semantic view of theory, models are seen as subordinate to theory and as playing no role outside the context of a theory. Well, yes, but we did say something about the relation between the syntactic, semantic, and the pragmatic view of a theory in the previous lecture. And we said that the pragmatic view of a theory can accept at least the semantic conception of a theory, but not restricting theory to the syntactic or the semantic conception. So although here it says that models are seen as subordinate to theory on the syntactic and semantic view, this is not entirely accurate, but we'll go along. This vision of a model has been challenged, obviously, in a number of ways, with authors pointing out that models enjoy various degrees of freedom from theory and function autonomously in many contexts. So this is the key point here, that those philosophers take models to be independent of theory. Now, independence can take many forms, and large part of the literature on models are concerned with investigating various forms of independence. So I'm going to name a few, and I'm going to focus on the last two. We have models as completely independent of theory, where let's say one is trying to study a specific system and one does not rely on theory but relies on certain commonsensical assumptions as well as mathematical equations. We don't have a theory. We're using a model independent of a theory. We have models as means to explore theory. I think this relates to the question of or to the topic of exploratory models, and models as complements of a theory, so they complete a theory, and models as preliminary theories. Here we're also related to the exploratory aspect of modeling. And last we have, or second to last, we have interpretative models, which we will say some more on later, and models as mediators. Now, interpretative models, this is important. So philosopher Nancy Cartwright argues that models do not only aid the application of theories, because many accept that models aid in the application of high-level theory. They are somehow incomplete. She claims that models are also involved whenever a theory with an overarching mathematical structure is applied. So theories of that kind are formulated in terms of abstract concepts that need to be concretized for the theory to provide a description of the target system. So what we mean by that is that we have a high-level abstract theory. And this high-level abstract theory requires an interpretation. What does the interpretation is the model. So the model takes these abstract concepts and fits them in a more concrete situation or more concrete theory to provide a description of a target. And we have models as mediators. So the relation between models and theories can be complicated and disorderly. This is what proponents of models as mediators say. Models, according to them, are autonomous agents in that they are independent from both theories and their target systems. So they exist on their own. And it is this independence that allows them to mediate between the two. Theories, we said earlier, do not provide us with algorithms for the instruction of a model. What is required is a detailed local knowledge about knowledge and material that are not provided by the corresponding theory. So in a nutshell, what does the model as mediator says? Well, it says that when we're doing science, we're trying to study specific systems. And abstract theories or theories are not directly related to these systems. What is related to these systems is models, representative models, which act as mediators between theory and systems, or theory and reality. The problem is that theories, even those who like theories, they know that theories themselves do not provide us with algorithms for the instruction of these models. So there's a lot of practical work that needs to be done in order to construct this model of specific theories. And these models are mediators. They enjoy a high level of independence from theories. In fact, success in specific situations depend more on the model and less on theories, because theories on their own, they're abstract. But even if you accept them as they are, they do not provide us with good explanations or predictions. You need the model. That's why models act as mediators. Now, models and other debates in philosophy of science. The debate over models affect other areas of philosophy of science. These debates, which were traditionally focused on theories, most of the philosophy of science has been focused on theories, now must consider the role of models, because we've realized that the different ways in which models are involved in science. For example, here we discuss briefly models, realism, the question of scientific realism, and laws of nature. So certain questions that philosophers need to and have thought about. So the use of distorted representations in models suggests an anti-realist interpretation of science. This is something we said when we discussed idealizations. We said, how can it be that, how can we take that that models explain if explanation depends on or requires truth, when idealization involves falsehood? Now, of course, we try to provide an explanation or a defense or a realistic defense, but this is something that there is no agreement on between philosophers of science. Some still emphasize that distorted representations in models suggest that we should have an anti-realist interpretation of science. Now, realists argue that models are approximately true and can be improved. Of course, the problem here is how to cash out approximate truth. And this is a big problem or big debate in the scientific realism debate, how to cash out approximate truth. Now, anti-realists respond is that there is no reason to assume that models can always be improved. The realist says, well, these models are approximation and we can improve them. The anti-realist says, what makes you so sure that you can improve them? Also, they note that scientists tend to shift to a different framework instead of the idealizing the model. So sometimes scientists might use idealized model, but they would not put the effort to de-idealize it. Sometimes they might shift to provide a completely different model, also that has idealization. Here we have a shift from model to model without the de-idealization. And that also most idealizations are not controlled. So why do we idealize? For different practical purposes, we need to do certain things. It's not like we know how or when or why to idealize. Sometimes we know, sometimes we don't. Also, we have the incompatible model arguments, also known as the problem of inconsistent models. Um, this argument states that scientists use multiple models of the same target for predictions, even if they contradict each other. But this is a challenge for realism. Well, why is that a challenge for realism? Well, if we have for the same system different incompatible models, and by incompatible I mean that assume that make different assumptions about ontology, what there is. Now, if we have different models and each model assumes different ontology, and all of these models can be used to make good predictions, let's say, it cannot be the case that all of these models are true, because what exists is a thing, is one. So if we have different ontology, we could not have different incompatible ontology unless an argument can be made. So let me try to re-explain that if it's not clear enough. So a single target system, we have a single target system, and the problem of inconsistent models says that sometimes, oftentimes, scientists use incompatible models, and by incompatible we mean models that postulate different ontology, to represent the same target system, although these different ontologies are incompatible. So something is not right there. And the anti-realist says, look, here's the problem of the incompatible models, or the problem of inconsistent models. We have inconsistency there. We cannot be realistically committed to any of these, because it could be that one of them is true. It could be that or one of them is faithfully representing the target system. It could be that none of them is faithfully representing the target system. Now, realists can respond by challenging the success of prediction of the model. So they might say, well, yeah, even if this model is used and it has provided good predictions, but it's not as good as the next model, and we will opt for the other one. But they can also adopt a more perspectival approach to modeling and say, well, although we have incompatible models, these models are providing perspectival representations. They're not providing representations independent of a perspective. But then the commitment would be to a perspectival form of realism. You cannot suggest the perspectival answer and accept a traditional form of realism. You would have to commit to a perspectival realism. Or you can deny the problem entirely and say, well, maybe we need more time. This is not, we're not committed to any of these, but at some point we will have a model that is able to do the work of both of these models, and we would sort the problem. But this is based on a hope and more and less evidence. What evidence do we have that the future model will be able to replace all of these older successful models? It's really optimism. Also, we have the nature of laws is also a focal point of realism debate. Commitment to laws of nature, with question arising on the role of law play if it is models that represent the world. So there's an implicit assumption here, which says that it seems that laws are playing a role in representing the world. Okay, but if models are what represent the world, then what role do we have for laws? Well, this is a challenge for proponents of laws of nature. And I wouldn't say that it's a big challenge. So one response could be that, well, laws apply to entities and processes in the model and not directly to the world. Another view considers laws to be open-ended statements that are filled during the building of the scientific model. So there are certain responses that could be had. What I forgot to say is that, and I should have said that earlier, is that the reason why I'm pausing at certain points and providing some of the responses of my own is that this lecture is largely based on the Stanford Encyclopedia entry on scientific models, which is written by Roman Frigg. So some of the things that he's written, I've integrated. Some of the things that I've written, I've responded to. That's why you see me pausing sometimes and challenging certain things which I'm not entirely convinced of. But definitely Roman's work is really, really good. That's why we rely on it. And I think, yeah, so now we can conclude. I hope that this lecture has given us some understanding on the role of models as indispensable tools in science. They serve multiple functions and they play a significant role in scientific discoveries, I said. And they are involved in representation, learning, explanation, understanding, and are connected in complex ways to theories. I hope that is clear. And the philosophical examination of scientific models reveal a rich landscape of different perspectives and interpretations that help us understand the nature of science. And this is very important because all of these lectures that I have been given is try to provide a more deep understanding of the nature of science. We spoke about concepts, we spoke about theories, and now we spoke about models. And as we progress with these lectures, I hope we would have a more a deeper understanding of science, nature of science, and how it works. Wallah subhanahu wa ta'ala alam.